Okay, today we are going to talk about interpreting graphs. Alright, so as a quick review from our last video on graphing by point plotting, we talked about how graphs can represent relationships between x and y. So today we're going to explore that a little bit more, right? And we looked at the example y equals x squared, and we looked at that graph. Then we looked at some points, right? X and y. Talked about that relationship. So today we're going to talk about when those relationships are functions. So, definition. A function takes in an input value and gives an output value. This is a very basic definition. We'll talk a little bit more about some rules that it takes for us to actually be a function, but at its most basic, this is really all a function is. I like to sort of visualize this in this way. So we've got our input x, we put x into some function. I'm going to call it f. F has a little lever. We pull the lever, and f spits out some y value. This is our output. And y we will sometimes call f of x. So we've got f with parentheses x. And again, we say f of x. This is not f times x, this is f of x, and this is what we got by putting x into f. Okay, so when looking at a graph, how can we sort of see this relationship? Let's look at this guy. Here and here. And our function kind of looks like this. I'm just kind of making something up. At, for instance, -3, right? At x equals -3. Let's say we're plugging in -3 for x. We put it into the function. We pull the lever, and what did it spit out? So if x is -3, then y is -2. That's all it means to be a function. So let's look at -1. Plugging -1 into f for x, right? Here x is -1. What is y? Y is 0, right? The value that we are next to on the y-axis is 0. So f gave us 0. All right, why don't y'all do 2? What do we get when we plug 2 into f? Well, x is 2. We look at y. Y is 1. So f gave us 1. Again, these guys are f of x here, right? And x's are given as our input here. So this is f of x is -3, so f of -3. Here, 0 is f of x when x was -1, so this is f of -1. And here, x was 2, so this is f of 2. For instance, if I asked you guys what is f of 2, the 2 being here, right, means x equals 2. So it's asking what is our y value, what is our output when our input is 2. So input 2, output 1. Easy as that. If f is -1 or f is -3, what do you get? Well, if f is -1, we said we get 0. If f is -3, we said we get -2. That's it. Okay, we can also work backwards. What are all x values such that f of x equals 0? Before, we were given x, right? We put it in, and we were asked what is our output. Our output is, and we found the y value, we got 1. Now, we're given the y value, right? We're given the output, and we're asked to find x. So, how can we do that? Well, we look at where is y equal to 0. These are all the points in the coordinate plane where y equals 0. We just need to figure out what points of the function are on this line. Clearly, it's this guy, right? What is our x value that gives us this point? Well, it's just 1. So x equals 1 is the answer. All x values such that f of x equals -2. Why don't y'all give that a shot? Okay, again, we want to look at where y is -2. So y is -2 here, right? These are all the points where y is -2. Where do we intersect with the function? Here. And what is our x value for this point? Well, it's -3. So we have x equals -3. You could have multiple answers to this question. You might have multiple x values that have the same y value. You might have no x values that have that y value, and that's okay. All right, so let's get some practice with this. Graph 2. What is f of -2? Well, if we look at that graph, every square represents 1, so we want to look along the x-axis for -2, so we count to the left 2, and we look for the y value there. The function is 2 units up. So the y value at x equals -2 is 2. Similarly, if we look for f of 0, we look at where x equals 0. That is the lowest point of that function, right? X is 0 right in the center, and we look for where the function is for y, and it's right there. So we're actually at y equals 0 as well. And then it asks f of 2. Again, f of x, we've replaced x with 2, so we're looking for where is x2? What is the y value? What is the output of the function when x is 2? So we look along the x-axis for 2. We move to the right by 2. We see that the function is up 2 units. So f of 2 is also 2. The last question here is if f of x is 0, then x equals what? So here, instead of being given x, right, instead of replacing x with something, we've replaced y, right? We know what y is, we know what our output is. We're trying to figure out what x value will give us a y value of 0. So first of all, we can think about in the coordinate plane, where is y 0 in the coordinate plane? Y is 0 in the coordinate plane along the x-axis, right? The x-axis has every point where y is 0. So where does the function run into the x-axis? Well, right in the middle, right? Right at the base of that. So what x value corresponds with that point? Remember, we're right in the center, so it's x equals 0. That is the answer. I want to look at the last part of graph 3. The last question is asking if f of x equals 0, then x equals what? So let's look at this one again. Where is y 0? Well, y is 0 at all the points along the x-axis, right? Those are all the points where y is 0. So where does the x-axis run into the function? We actually have multiple points where this is the case, and that is actually okay. We can have more than one x value that gives us a certain y value. That's totally fine. And in fact, we want to list all of them. Looks like the first one is -4. The next one, as we move along, looks like we hit it right in the center, so that is 0. And then it comes back down again at x equals, it's 1 to the right, so just 1. Next question I want to look at is graph 5. All right, first question is asking, what is f of -3? So again, we look for where x is -3. We want to move along the x-axis 3 to the left, right? So 1, 2, 3 over. We look down. It's really kind of unclear exactly where that is. We can't be super sure, so we can just make our best guess. So I'm going to say that maybe that's like 0.3 down. If you come across something like that, just make your best guess. I promise to give you credit. I will never take off points for something that was unclear. So 0.3 is a great answer here. Oh, sorry, -3. -0.13, right? We're down. You could have said -0.25, -1/4, -1/3, something like that. Anything close. Totally fine. Okay. What is f of 0? Well, we look at where x is 0, right? X is 0 along the y-axis. The y-axis runs into the function just below, right? Just 1 down, exactly 1 down. So it looks like our y value there is 1. Next, what is f of 1? What's going on when x equals 1 here? Well, we look to the right, 1, along the x-axis. We look up and down, and we see that we've got that weird, funky thing going on that we had when we were looking at that graph of 1 over x in the last lesson, graphing by point plotting. Again, so something really funky is going on. We haven't talked about it necessarily, but we do know that there are no points for that x value, right? It's undefined there. As we come in from the left, it's getting really, really, really small. And as we come in from the right, it's getting really, really large. But both of them look like they're not touching x equals 1, right? So there are no points at x equals 1. So f of 1 is undefined. You could also say does not exist or none or whatever. Since a lot of our assignments will be, or since all of our assignments will be online, usually they'll let you know what exactly you need to put in for it to be counted correct. Last question here. So if f of x equals 0, then what is x? Remember, y is 0 along the x-axis, right? Those are all the points where y is 0. So we want to see where the function is running into the x-axis. And we look at the graph, and it's getting really, really, really close, but it's not touching it. What x values give us a y value of 0? This function never has a y value of 0. So there are no x values that give us that. So x equals, you can say DNE, does not exist. You can say none. I'm going to write none here. Next definition. The domain of a function is all possible input values we can put into that function. Input values come from and make up our domain. They're represented by an independent variable which is usually x. But sometimes it'll be other things like t or a or really anything. Let's look at a couple of examples here. Again, we are talking about domain. So if I have a function that looks like this, let's say we've got -5 and 2. And I ask, what is my domain? So we are just looking for every x value that is associated with this function. So what I like to do when I'm looking for a domain is scan along the x-axis, right? and see, do I have any function above or below me? As I'm scanning from left to right, I start here, I'm looking up and down, there's nothing above or below until I get to -5. When I get to -5, I've got this open point here. Again, it's open, it's not included, but it does start at -5, so I'm going to mark that with a open point. Then everything to the right of -5, right? All of this has function above or below it. So I'm going to, I can, if I want to, keep track of it by shading along the x-axis. This is not something that I'll ever ask you to do necessarily, but it sometimes is helpful. Our function is continuing forever off to the right and up, so we know that the domain is going to continue. So the green here is representing all of the x values that are input for the function, so this is our domain. Now, the useful part about doing things like this is that it's really easy to see the interval notation of the domain. So we have this open point, so that means we're going to start with a parenthesis, -5, and then everything else is included all the way off to infinity, right? It continues off in that direction. So we're going to go to infinity, and then infinity always has a parenthesis. If you don't feel super comfortable with interval notation, I would recommend checking out the just-in-time WebAssign assignment called Just-in-Time Interval Notation. It's a really helpful refresher. Yeah, we're going to keep using interval notation really heavily all semester, so definitely good to get a handle on it earlier rather than later. Okay, next function. Let's say we've got just kind of a line segment like this. And this point is, let's say, -3, -2, and this point is +2, +1. Okay, so again, we're looking for the x values associated with this function, so we can do that by scanning along the x-axis from left to right. So we start, there's nothing above or below here until I get to -3. And then I have a point at -3, right? It has an output value associated with it. So because it has output, we can record this guy, we can shade it in. Then everything to the right also has some function, has an output value associated with it all the way until we get to 2, right? When we get to 2, we have this open point, so there's no output here, so we have to leave that one open. But everything up until 2 is included, so we want to use that open point. All of this is our domain. And we can write this in interval notation. The closed point here is a bracket, -3. And we continue all the way to the 2, parenthesis, and that is our domain. Last but not least, let's look at one more example super quick. Let's say we've got this classic guy that we've seen a few times at this point. So again, looking for my domain, I start on the left of the x-axis. I look up, I see that the function is continuing forever, right, in this direction. So all of these are going to be counted. And there's function all the way through. We get to the other side, we see again the function continues all the way to infinity, right? It's continuing off forever. So looks like we have the whole entire line shaded. So our domain of this function is actually all of it. Domain. So this in interval notation is, right, we're starting at kind of forever in the negative direction, also known as negative infinity, and we're continuing to forever in the positive direction, which is positive infinity. Often call this colloquially all real numbers. Okay, let's go back to these examples from before. Again, these are in the lab manual. This is the Interpreting Graphs 1 lesson. So if I look at graph 2, what is my domain here? Just for the sake of this lesson, we're going to assume that there are arrows at the top. There really should be arrows. But we're going to assume that it continues. So if I'm looking along the x-axis, I can kind of see that any x value that we look at, right, we start at negative infinity, we move to positive infinity, all of those have function above it, right? So our domain here is going to be all real numbers. And same goes for graph 3, right? Again, we can assume that we have those arrows even though they're not really shown for the purposes of this lesson. And this one also, covering all of the x values. If we look from left to right, graph 5, so this one is a little bit more interesting. So as we move along the x-axis from left to right, at the left side, we look down, we see the function is right below it, getting really, really close. So that is definitely going to be a part of our domain. We continue along to the right until what happens? So again, remember we talked about it at x equals 1, right? We had this undefined situation, right? There's no output at x equals 1. So because there's no output there, that is not going to be included in our domain. So how can we write that? We want to write infinity all the way to 1, not including 1, and then 1 to infinity, right? We start that by writing parentheses negative infinity, and then we go all the way up to 1. We don't want to include 1. To not include something, we use a parenthesis. And then we've got to include that second piece to the right, right? So once we pass 1, the function picks up, again, really, really large number at first, and then it gets small pretty quickly. So that happens right after 1. So in order to write that in there, we are starting at 1 but not including 1, and then moving all the way to infinity. Again, interval notation will help with this, but that is our domain. Okay. Sometimes domain is stated explicitly. And for example, let's say I have f of x equals x squared, comma 0 is less than or equal to x is less than or equal to 5. So this is a part of this function. This is a explicit statement of the domain of f. And what this is saying is I'm looking at the graph of the function f of x equals x squared, right, which looks like this generally. Ugh, that is I'm trying my best, y'all. But I explicitly only want to look at the x values between 0 and 5. So actually, what this function looks like is, let's say this is 5, this. So it looks like really just a chunk of the rest of that function. So for this guy, the domain is 0, right? Because 0 is included, right? We're less than or equal to 5. Definition. The range is all values that are output of the function. Output values come from and make up our range. They're represented by a dependent variable usually y. You've got independent and dependent variables. You might have heard about those in science class. Maybe it's been a long time. So our independent variable, x, right, is our input. Independent input, maybe that's helpful. Our y value is our dependent variable. Our y value depends on what we put in for x. When we get to talking about word problems, this is going to show up a little bit more because a lot of times in word problems, x, or our input, is time, right? And time doesn't depend on anything, right? Time is going to keep going no matter what. And then whatever is happening is going to depend on how much time has gone by. Independent input, dependent output. Let's look at a couple of examples of finding range. So if we look back at those same examples from before, we're looking for range. So looking at this first guy, again, we want to sort of move from negative infinity to positive infinity. Before, when we were doing that along the x-axis, that meant we were moving from left to right. Now we're moving from bottom to top. So starting at the bottom, moving up, I look to the left and right, and I see nothing, right? There's no function here. So the first y value where we have any function even close to it is this -2, right? -2 has the point right on it, right? So this guy is definitely going to be included, right? At the bottom of this parabola, we have the lowest point. The lowest point is at -2, so we fill that in, and we continue up. The next time we have something going on, anything interesting, all of this clearly has function next to it. We've got something interesting going on at 2. We have this open point. So if I have that open point, does that mean that 2 has no function associated with it? No, right? Because this guy, right? we do have an output value of 2 over here. So 2 actually is included, and we continue all the way to infinity, right? The function is going up forever, so we are continuing. So our entire range, this is our range. It continues up. Range. Again, we want to write it in interval notation. We're starting at -2 and continuing to positive infinity. We are including that -2, so we've got bracket -2 to infinity. All right, this next guy, we're starting at the bottom, we move up. First thing we have is -2, so we can mark that guy. And we can continue up, right? All of this has function associated with it, right? All of these y values are output of the function. Then we get up to this 1, right? And this is an open point. We look along that line, y equals 1. The function never intersects it, again, after that. So we can mark that as an open point, and that is the end of our range. So this is our whole range right here. So we're starting at -2, and it is included, so we have a bracket, -2 to 1, parenthesis. And last one, we have this guy again. We start at the bottom and we move up. We have no function associated with this y value, we have no function associated with any of these y values, right? So we look to the right and left and there's nothing going on. None of these intersect with the function at all, until we get to y equals -4, and then we have this point right here, right? There is a point at the bottom of this guy. I don't know what the x value is. We could make something up, right? Because I made up this graph. But it is at y equals -4. So y equals -4 is our first point that we want to shade for this guy. And then we continue all the way to positive infinity. All of that is our range. Continuing range. And this guy starts at -4 and continues to positive infinity. Let's look at these with our examples from the lab manual that we've been looking at. So the range of graph 2, I'm just gonna write RNG. What is the lowest point on the graph? It's the bottom of that sort of valley, right? Of that quadratic function. That's the lowest point on the graph, and it has a y value of what? Has a y value of 0, right? So we're starting at 0, and it is included, right? Because the bottom of the quadratic function is a point, has a y value of 0. And then it continues upwards forever. So to infinity. Graph 3, we look at this guy. This is a polynomial, right? It's continuing from the left side of the graph to the right side of the graph, and it's curvy. That's how we know something is a polynomial. It doesn't have anything super funky going on, it's just kind of curvy. So this guy has a range of, well, if I start at the bottom of the y-axis and I look to the left and right, there is some function, right? If I look to the right, there's function that is continuing all the way down forever to negative infinity, right? So all of those y values have function associated with them. I move up the y-axis and off to the left. We still got function, we've still got function, we've still got function. There are a few y values in there that have 2 or 3 points associated with that y value. For instance, at 0, like we saw before, there are 3 points associated with y equals 0. So that is definitely included. As I pass over those sort of peaks, right, we still have function off to the left, so it still counts. So the range of this function is all real numbers. Awesome. Now looking at graph 5. So we start at negative infinity. We have some function very close to it, right? And it's got that arrow pointing downward, so we know that it's going to continue forever. So we definitely are starting at negative infinity. Then we move up until we get to 0, right? And then the function gets really close to y equals 0, the line y equals 0, also known as the x-axis, but it doesn't touch it. So we know that we're not including 0. So we do 0 and then a parenthesis. Union, then we have the second chunk, right? When we look off to the right, along y equals 0, we've got that piece that's coming in and moving up. So again, not including 0, but everything after that. And then we're going all the way up to infinity so that we've got that arrow that's pointing up, so we know we're going all the way off to infinity with a parenthesis. Infinity always has a parenthesis. Back to the notes. Each input value is associated with an output value. And you might not recognize it yet, but there is one word in this sentence that's just a little bit more important than all of the other ones. And that word here might be a surprise. It's and. Normally not a super important word in a sentence, but here it's very important because what it's saying is that we have exactly one output value associated with any given x value, right? If I'm looking at this representation of what a function is, right, if we're looking back at this, whatever x I'm putting into my function is going to give me one y value. It's not going to fork off and give me 2 y values. It's going to give me 1 y value. So, for instance, for example, let's look at some point on a graph of some function f of x. Doesn't really matter what function, but we know it's a function. Let's say that point is, I don't know, 1, 3. I'm just picking anything. 1 is the input, and 3 is the output for that input. So putting that into our sort of function representation, right? 1 went into the weird function machine, we pulled the lever, and we got out 3. And 3 is f of 1, right? That's just kind of refresher on that function. F gives at most 1 output. So that means I can't put in 1 and also get 2, or also get 5, or also get even something really, really close to 3, like 3.0000001. None of these can also be on the graph of f. Okay, so that means, right, I'm looking at f. This isn't even really super necessary for you guys to draw, but, right, I know I have the point 1, 3. I know I can't have any other points here, right? None of these points can also, these are all the other points that have the x value of 1. None of them are allowed to be a part of the graph, right? So it doesn't matter what's going on in the other places, right? We could be going up, we could be going down, we could be keep staying straight, doesn't matter. We could stay straight for a little bit and then go down. Who knows what's going on? As long as we don't cross this line again, right? So because of that, we know that if I look at any vertical line, I should only pass through the function maximum 1 time. So if I was going to test if something was a function, right, I could just check a bunch of vertical lines, right? Check and make sure that there are no vertical lines that pass through the function more than once. We just invented a test to see if something's a function. Let's name it something super, super creative and really fun and really original. Like, I don't know, vertical line test. A graph passes vertical line test. We'll abbreviate that VLT pretty frequently. If every vertical line hits the graph no more than once. And very important fact, a graph represents a function if and only if it passes VLT. And while we're at it, it's not going to be super, okay, while we're at it, let's just go ahead and write something called the horizontal line test. It'll be important later, I promise. A graph passes HLT if every horizontal line hits no more than once. Again, this will be much more important later, or you'll see why this is important later. But if a graph is a function and passes the horizontal line test, it is called one-to-one. Okay, so real quick, let's go back to these guys from the lab manual. Graph 2, is this a function? Let's look at it. Any vertical line we were to pass through that would only hit it once, right? So this guy is a function. I'm a function. Is it one-to-one? If we pass any horizontal lines through it, what happens? Most of them hit it twice, right? A lot of them hit it twice. So I'm not one-to-one. Graph 3, same deal, right? What about graph 5? So I pass any vertical line through. What happens? Well, most of it is a clear, only passes once, right? The only place that's maybe a little bit suspicious is x equals 1, right? So let's look at that part. Remember, we've got it going all the way down, right? And on the left, and we've got it going all the way up on the right. So I guess our only possible fear is that maybe they might end up being on top of each other. But remember what we said, we never actually touch 1, right? We don't have any points at x equals 1. So actually, these guys are split. So we are totally good here. Graph 5 is a function. I'm a function. Is it one-to-one? Let's look at the horizontal line test. Same deal, right? Every horizontal line we pass through looks like it only passes through once, which is totally great. The only place that's tricky is y equals 0, right? That horizontal line at y equals 0. But again, remember, we're getting really, really close to y equals 0, but not touching, so these guys are separated. So I'm also one-to-one. Okay, one that I want to look at now, that we haven't looked at yet, is graph 6. So does this graph represent a function? Let's check the vertical line test. Do any vertical lines passing through this hit the graph more than once? Yes, totally. A bunch do, right? So this guy is not a function. Is it one-to-one? Great question. Let's try the horizontal line test. Let's pass some horizontal lines through it. Do they hit more than once? None of them do. So we pass the horizontal line test. Does that mean that we're one-to-one? Really quick, let's take a look back at our definition of one-to-one. A graph is called one-to-one if it is a function and it passes HLT. So we did pass the horizontal line test, but it's not a function, so it can't be considered one-to-one. Not a function, not one-to-one. Okay, last example. I want to look at the first question on piecewise functions. All right, so we've got this nice graph. It's a little funky looking, but we don't want to let that scare us. It will be a little bit more challenging, but not by much. You guys totally got this. So we're looking first for the domain. All right, so I'm looking along the x-axis, and I'm looking up and down for where we have any function associated with it. Do we have an output value? I'm looking at the very left. Do we have an output value for all the stuff on the very, very left? Nope. There's nothing on the very left of the function above or below it. So we keep on moving to the right. The first x value that we have function for is what? -5, right? -5 is going to be the first piece of our domain. Is it included or excluded? It's a closed point, so we are going to include it by using brackets. All right, let's keep moving. So we keep going, nothing changes, everything's fine until we hit 1. At 1, we have some funky stuff. We've got 2 open points, one on top of another. -5 to 1. Because there's no output at x equals 1, 1 is not included in the domain. So we want to exclude it using a parenthesis. Then we move to the right a little bit more and we have another chunk of the function. So we want to start a new chunk of the interval. That function starts in a different spot, but it is still starting at 1, right? But it is an open point, so we don't want to include it, so we're going to use a parenthesis. And then we move to the right, and as we move to the right, we see we've got some stuff. We got a bunch of stuff all the way until we hit 6. And at 6, we have an open point, so we use a parenthesis. What is the range? With the y-axis, we're moving from bottom to top. The first y value that we have output for, the lowest point on the graph, is the point -5, -1. Our range is going to start at -1. That is a closed point, so it is included. We move up, and we can finish out this chunk if we want to. We can definitely put them separately. That's totally fine. This chunk ends at 5. And 5 is an open point, so we can put a parenthesis there. The second chunk, right, starts at, I'm going to guess that that's about 1.5. And it's also open, so we are not going to include it. And then we're going to continue all the way up to, that looks like 19. Also not included. If you wanted to, you could actually write this as -1 all the way to 19, because like we said before, right, when we're looking at the output value of 5, yes, it's not included on that one chunk, but it is included on the other chunk. So we can just sort of skip to that other chunk and say, oh, I'm just continuing all the way up to 19. Either of these are correct and will be accepted. Okay. Next question. What is f of 0? It's asking us, where does x equal 0, or what's going on at x equals 0. So when x equals 0, right, we're looking along the x-axis for 0. X is 0 right in the middle, right? And so we look up, and the associated output value is 4. I know the next question says f of 3, but I want to ask a more interesting question, which is, what is f of 1? What is f of 1? Well, let's look at 1. 1, of course, is 1 to the right of 0. Along the x-axis, we look up. We've got not just 1, but 2 open points. Open points mean we have no output value. So f of 1 is undefined. Wah, wah. if f of x equals 0, x equals what? Well, f of x equals 0. We want to look for all of the points where y is 0. That happens to be the x-axis. We look along the x-axis to see where it runs into the function, and it looks like we run into the function at x equals -4. Last but not least, if f of x equals 5, what is x? Well, let's look at the line where y equals 5 is a horizontal line that runs into the y-axis right at 5. If we look along that line, we kind of, in some senses, run into the function in two places, right? We run into it at that open point at 1, 5. We also run into it at, well, around, I want to say that's like 2.5-ish. So what's the x value? Does the first one count? Does that open point count? Is that an x value that gives us a y value of 5? No, it is not, because it's an open point, right? It's not included. So our only x value that gives us 5 is 2.5-ish. All right. Hopefully this was helpful. And thanks for watching, you guys.